Morning, everyone. So over the last 2 days, we started looking at buffer systems. So let me just rehash a couple of things here. To be a buffer, they are solutions containing, they keep using this word here, appreciable amounts. There's enough that you can appreciate that there's stuff there. Appreciable amounts of either weak acid and beefing up the conjugate base. That would end up giving you what's called an acidic buffer. So it's something that buffers in the acidic region. Or you can have similarly a weak base with a conjugate acid, and that gives you a basic buffer. Remember, this terminology here of acidic or basic buffer doesn't mean you can only buffer one direction. To be a buffer, you need to be able to maintain pH in both directions. So weak base and conjugate acid, that resists. You do want to emphasize this: large changes. There is still going to be a change. Large changes in pH, and also specify upon small additions, assuming you don't max out your buffering capacity, small additions of acid or base. Again, a couple key emphasis here is we know we need it to be weak because we know we need an equilibrium system. It's because of the shifting that's going to be able to moderate the pH for you. The pH will change. It's not going to change largely, and there is a limit to how much acid or base we can add. So there were two ways of making these buffer systems. The easy way here is just start off with the something that's weak. So let's say acetic acid. This thing here is a weak acid, so it's going to be in equilibrium. It does release off a proton, but because the Ka constant is so tiny, the bulk of the weak acid actually stays on this side. If this one here started off, let's say at 1 molar, we're only going to get a really tiny X that actually goes over the other side. It's not that the mole ratio doesn't work, it's just that in comparison with the numbers, only a really small fraction goes over, so that reactants are still favored. So far, this one here can shift to the right because I do have acetic acid, which means it can currently resist additions of hydroxide. If I add hydroxide, it pulls the H plus down. That ends up forming water. As it pertains to the initial equilibrium, it ends up shifting the whole equilibrium to the right. No problem, I have enough acetic acid. But again, to be a buffer, you need to be able to buffer both acid or base. So far I've added base. What if I add acid right now? If I end up adding acid, the H plus is trying to go up. It is in equilibrium, it does want to respond, but I really don't have a lot of CH3CO minus. That's going to limit the impact of this buffer system. So that's why we need to beef up the conjugate amount here. The easier way is just add in the salt. So make a mixture of, so we had acetic acid, throw in equal parts, maybe sodium acetate. Where did the sodium come from? That just guarantees it's a soluble salt. More on that in this lesson here. But basically you just mix the two together. That's one way of doing it. Yesterday we started looking at a little bit more complicated way of doing it here. Basically what it involved was eventually we do want to have this equilibrium where we have good amounts of both the conjugate acid and conjugate base, but what we did is we actually ran it through a neutralization. So let's take our acetic acid again. We're going to do a lot more of this stuff here in the coming lessons. We took NaOH, which is a strong base. We actually used it to neutralize off some of the acetic acid. We know the neutralization reaction. When you hit a point called equivalence point, basically I've killed off all the acetic acid, but just sort of big picture here, we may have started off with just weak acid. I gave you numbers from previous. Maybe I had 10 molar acetic acid here. We start off with no sodium acetate, right? This was not a salt that I add in. But upon adding in hydroxide, the hydroxide will slowly kill off the CH3COH. I'm going to rehash this main term here. At the equivalence point, also called the stoichiometric point. Careful, this one here is different from what's referred to as the end point and the transition point. Those are referring to indicators. We'll get to that. But at the equivalence point, because this is the acid-base neutralization, we have a situation where the moles of H plus has perfectly matched up to the moles of OH minus. The reason why we call it a stoichiometric point is because you have just added in. We initially started off with all acid particle. You've just added in the right amount of base that it follows the mole ratio. In this case here is 1 to 1. So I've added in equal part. So it perfectly cancels out. That happens at equivalence point. At equivalence point here, it's like that titration point where that's the point you want to stop. That's when there's no excess, and that's when you can actually do your calculations. Every time you're at equivalence point, since we killed off the acid and we killed off the base, we would expect that the pH is going to be 7. We learned last day for this equation the pH was actually above 7. pH was actually slightly bigger than 7 at equivalence. We'll come back and we'll talk about why that is in today's lesson here. But as it pertained to buffers, what we ended up doing was, since you had 10 molar to start off with, I know you would need 10 molar to completely have it at equivalence point. What if I don't give you all 10 molars? What if I'm at a point called half equivalence? So if I'm halfway to the equivalence, I would have only added in plus 5 molar NaOH. The plus 5 molar NaOH here would completely get consumed. It's going to convert some of the conjugate acid over into conjugate base form. I still have some leftover reactant in excess here. So I have 5 molar of my conjugate acid, and now I may have also 5 molar of my conjugate base, and therefore I have another situation where I have appreciable amounts of both. I have naturally created a buffer system. We did study that in terms of a curve. We're going to do titration curves a lot more in the upcoming days as well. But basically what we had is, we had a weak acid. We expected the pH to be something less than 7. So pH, what I'm doing is I'm adding a strong base. I don't want to worry about any equilibrium problems with the base. Basically, I would have expected the pH to jump because I'm adding a base, but we notice that as I approach this half equivalence point, there is a situation. I know my number may not be as high as it was initially, but still 5 molar is quite appreciable in both. There will hit a point here at the half equivalence point where we're perfectly a buffer system. This is at that half equivalence point. We'll call this half the volume for now. It's going to buffer around here. Basically, if you add base, as you add base, it's going to try to kill off some of this H+. Well, I have enough acetic acid to actually shift over. It doesn't let the pH climb by that much. If I add acid to try to go in the opposite direction, it doesn't let it fall by that much. Wherever the pH sort of levels off here, that's called the buffering capacity, and that was just naturally formed. I didn't need to beef up the conjugate base form myself. That just actually came out of the neutralization reaction. Once you're out of the conjugate acid, where I don't have any more acetic acid to actually react, then adding base here will suddenly make this jump upwards, and it's going to level off again. Today, I just want to revisit this whole notion. How come, while we're at equivalence point, this is a very important term for you to know. Equivalence point is moles of H+ equals moles of OH minus. Everything's cancelled out. How come if all the reactants are gone, everything's perfectly neutral? How come the pH at equivalence point, when the pH suddenly jumps upwards, how come the pH is actually higher than 7? Okay, so we're going to do this as a sort of side note here in a lesson we're going to call hydrolysis. Hydrolysis, essentially, because water is such a common solvent here, there's going to be many names that we give to water reactions. So hydro means water, and lysis has the notion of breaking. And essentially what we're going to do here is we're going to actually analyze a few different salts. We're going to dissociate the salts here in water, because that's what water does. It breaks up the positives from the negatives. Depending on those positive and negative, salts are not supposed to be acidic or basic unless they have H+ or OH minus, and yet sometimes the salts themselves, the ions that end up forming, are themselves either conjugate acids or conjugate bases. That way we can actually predict why the pH is actually higher or lower than 7 at equivalence point. So let me just give you an overview of what we're going to do. We're going to take a salt, let's say it's AB. First thing that you're going to do, this is probably the most systematic section in this chapter. Basically, you could always do this procedure. You're going to, upon putting in water, you could dissociate the salt. Maybe I get A+ and B-. After you dissociate it, some salts, the ions themselves are conjugates of strong acids or strong bases. They have actually no chance of actually going in the reverse direction. So in that situation, they're going to be spectators. After we've dissociated them, we're going to cancel out the spectators. If you're not a spectator, then you're going to check the table. And that's generally the procedure that we're going to be after. Sometimes if they're both spectators, neither of them can react with water. It's not going to be acidic or basic. But if these ones here themselves are conjugates, they might end up replenishing a little bit of acid or a little bit of base, knocking the pH slightly different. So let's just step our way through here. The hydrolysis of a salt is a reaction between water and not just the salt, right? Water has already broken up the compound, but it's water and the cation and the anion. Remember, cation here is the positive charge, cats are positive, anions are the negative charge here, or it could be both, so as to produce an acidic or basic solution. So, note, we're actually not considering just the solid itself, we're considering it's the ions that end up dissociating, breaking off from the solid. It's not the solid itself that we're worried about. The conjugates of strong acids and strong bases are referred to as spectator ions. We did see these spectator ions a little bit with the net ionic stuff with our KSP section, but basically spectators, like spectators at a hockey game, they don't, they are unchanged before and after. They look identical when they're on the reactant side or on the product side. Okay, so if they are spectators, this is what we expect for a salt. There's no reason for your cation or anion to replenish H plus and OH minus. If both of them are spectators, if they both don't participate, we end up having a neutral solution. So they just want to rehash that there. They're using that term here, spectators. If they are spectators and they no longer participate in a reaction with water, we would expect the solution to stay neutral, right? We have been learning this chapter here on acids and bases. Acids knock the pH less than 7, bases knock it higher than 7. If these things here aren't acids or bases, I would expect the pH to be exactly 7 at 25 degrees. So let's just look at some strong things here. So NaOH, this is a soluble salt, and it contains hydroxide. So this one here is a strong base. We can indicate that because it's a one-way arrow, pretty much all the NaOH would break off and end up forming this hydroxide. So this NaOH by itself would definitely knock the pH very, very high above 7. The conjugate of this strong base here would be like the Na+. This Na+ here would be referred to as a spectator. Na+ cannot recombine with OH minus, right? It's on the product side here. The arrow is headed one way towards them. They can't actually go in reverse. Cannot recombine with OH minus because the NaOH is too strong. Right? That's a one-way arrow, not an equilibrium, so definitely not a buffer system. So therefore, we can refer to Na+, this conjugate here, as a spectator. Similarly here for a strong acid, because it's a one-way arrow, 100% ionized, once I actually break up to form H plus and Cl minus, there's no going back. The Cl minus cannot react with H plus and go in reverse because it's actually a one-way against it. So chloride here, not only can it not recombine with H plus, more to the point with this hydrolysis section, chloride cannot react with water, right? It could potentially, right, there's a lot of water in solution, it might potentially grab a proton, but in this case here, the grabbing proton reaction will be proposing the reverse reaction, and right now definitely for a strong thing, it's a 0% reaction in reverse, okay? So, these are common spectator ions pretty much in this hydrolysis section. These are the ones that we're going to ignore later on, okay? So spectator cations. Spectator cations, positive particles, typically we're going to look for group 1 and group 2 metals. So these ones here typically are going to be soluble salts. So once you get them in water, they are present, but they're not really going to interfere. They're not going to react with water. Any group 1s, so your alkali metals, so sodium, lithium, potassium, okay, those ones there, or even your alkalines, many of which are actually soluble. So those are the positives that we're not going to worry about. What about the anions? The anions are a little bit harder. We actually do need to consider it's the negative ion that came out from a strong acid. I'm just going to list for you the strong acids that we have. We have HCl, we have HBr, HI, HNO3, HClO4. Okay, these ones here are the strong acids that we have. These ones here are all leveled by water. They're all one-way arrows. They're going to be able to release off of H plus no problem, and they're going to be counterbalanced by their corresponding ion. So these ions in particular, you can memorize them. These ones here have no chance of going in reverse. So these ones here are going to be spectator ions. Now, you might remember there's actually one other strong acid. Sulfuric acid is actually a diprotic acid. Diprotic acid meaning it actually has two potential footballs to give. Sulfuric acid is only strong in the first protonation. So it can lose an H plus, but it still has an H to give. This one here is not a spectator, as we're going to see in this lesson here. HSO4 minus itself is actually a weak acid. So although technically you do have 6 strong acids here, it's only those top 5 that are kind of spectators. The HSO4 minus is definitely not a spectator. Okay, so let's just have a look here. We're going to deal with anionic hydrolysis first. So once the solid is dissolved, if the anion is a conjugate base of a weak acid, right? If it's a partner of a weak acid, it will gain a proton. It'll re-grab the H plus to hydrolyze water. Okay, so let me just give you an example of that here. Let's start off. I'm going to leave myself a little bit of room here for cationic hydrolysis. Let's start off with a chemical here, NaCH3COO. Okay, like I mentioned, at the end of the day, this part here is the most systematic. It's the same steps no matter what you do. We're going to have our sodium acetate as this example here. Always ask yourself, anytime you're given a chemical, what is this? Is it an acid? Is it a base? Is it a salt? In this case here, you see it's a, well, metal and non-metal. It's a salt. In fact, it's an alkali salt. So this is going to break up to become Na plus and CH3COO. Salts have no business being acids or bases. We would expect the pH to be neutral. We've dissociated the salt. Next thing what you're going to do is you can cancel out any spectators. We just said group 1 ions tend to be spectators. So this one here is a spectator. It's just going to sit around solution. It's not going to do anything. If I'm a conjugate of a strong acid, I'm also a spectator. Comparing my list, acetate here is not actually on this list. So because it's not a spectator, it potentially can hydrolyze. This is called anionic hydrolysis because this one here is an anion. What is CH3COO minus the conjugate base of? Well, upon reacting with water, we know it's weak, so it's going to be in equilibrium here. This is going to end up reforming acetic acid when it reacts with water, when it hydrolyzes, and it's actually going to produce some extra OH minus. So this is actually what was happening in our very first example here. We had a situation where, wait, the base killed off all the acetic acid. We were at equivalence point. All the reactants are gone. This salt here that we end up forming had no business to be acid or base. It just turns out when this one here is soluble, when it breaks up, the acetate here is actually a weak acid, and in grabbing the proton from water, it ends up regenerating some acid and ending up creating some more hydroxide. Even though we were at equivalence point, we had expected the H plus to have perfectly cancelled out the hydroxide. We've now reformed some OH minus. So I can write in words here, the salt has reformed some extra OH minus at the equivalence point. Equivalence meant the reactant acid and the reactant base here had perfectly killed off, perfectly neutralized, but it's just the salt itself actually as forming the hydroxide. So anionic hydrolysis typically ends up forming a basic solution, or you can say a pH bigger than 7 at equivalence. Remember, this one here is weak. We had done all those Ka, Kb sort of calculations here. Because our constants in general are very tiny, this equilibrium here does not break up very easily. So the small fraction of acetate that ends up reforming acetic acid, reforming hydroxide here is not all that great, but it's enough to knock the pH slightly into the basic region. Now don't worry about, wait a second, I've also created the weak acid. Wouldn't this one here also end up forming H+? Well, if potentially this one here wanted to go backwards and reform the H+, there's even less of it that actually protonates off. So usually once you write the reaction, here's the ion, here's the hydrolysis with water, figure out whether it's produced OH minus, in this example basic, if it ends up producing H plus overall acidic, as we're going to see for cationic hydrolysis. Okay, so case in point here for cationic hydrolysis, we're going to look out sometimes if the cation, the positive part from the salt, if the cation is the conjugate acid of a weak base, overall cationic hydrolysis, the solution becomes acidic even at the equivalence point. At the equivalence point here, we were supposed to have killed off all the reactants. There's no acid, no base left. But if the salt itself actually regenerates a little bit of H+, the pH here is going to be less than 7. So let me just give you 2 examples of that here. First one, let's do NH4Cl. Ask yourself, what is it? Okay, well, this one here is a salt. It has no business being acidic or basic. It's going to dissociate. We're going to get NH4 plus, and we're going to get Cl minus. The salt here is completely ionized. Hydrolysis is not, well, water breaking that up. I know that part already. We want to decide which one of these here are spectators. Well, chloride is actually the conjugate anion of a strong acid. Chloride has no chance of picking up the proton to become HCl. So this one here is a spectator. The ammonium is not, though. Ammonium is actually the conjugate acid, NH4 plus, in the presence of water. It's going to some extent, it's going to be able to break off, reforming NH3 and providing for you some extra H+. It's that extra H+ that's going to knock your pH actually into the acidic region, pH less than 7 at equivalence. Okay? So Pretty much if it's the positive that ends up hydrolyzing, it's probably acidic. The negative that hydrolyzes is probably basic. Now there are a few things to be careful of. There are a few metals. Let's say my example is going to be, let's do aluminum chloride. You may remember from our sort of periodicity chapter here, aluminum compounds, they're sort of middle ground, they're sort of ionic, sort of covalent here. If they were sort of more on the covalent acidic side here, I would expect the solution to end up generating H+. And yet the question is, well, how does this thing here produce H+? We have to remember for this AlCl3, right now it's a salt. Water is going to separate them. Water is going to make it Al plus 3 and 3Cl minus. I'm actually going to tell you that this is acidic, so it's not the anion that actually hydrolyzes. This one here is a spectator. It must be this Al plus 3. But how is this Al plus 3 supposed to release H+? It doesn't even have H+. First thing is Al plus 3 is a really high charge, so it's not going to be very soluble. Charges in general are unstable. We note that aluminum actually doesn't stay as Al plus 3 by itself. It actually gets surrounded by water. This is where water, last year we had called them ligands, this year we can call them Lewis bases. Water is a polar compound. It's going to surround this aluminum from all sides. Essentially, aluminum is actually a complex. Aluminum is surrounded by 6 waters. That's our most common geometry, octahedral geometry. Water overall is neutral. It's trying to stabilize the plus, but being a neutral compound, it can't get rid of the plus. So this one here is still a plus. And now what's going to happen is, now that the water has actually data bonded and coordinate bonded, it's actually weakened some of its other attachments. And basically what's going to happen here is we're going to lose some H pluses here. Previously, the Al plus 3 had no business giving off H plus. This one here, as a complex ion, we still have aluminum. We still have 5 waters that were untouched. There was 1 water that I pulled off an H+, so there is an OH grouping. If that OH can be released, it would be basic. But in this case here, I'm actually having lost an H+, so overall this solution here is acidic. My charge would have gone down by 1, so we're actually a +2. Okay? So, again, it just generalizes for you there. Typically, positive ions, cationic hydrolysis, ends up forming acidic solutions. The salt, which had no business being acidic or basic, is actually acidic. So, this one here, there's 2 other really common examples that they usually do. If they throw in iron or they throw in chromium, same story, these will end up forming acidic solution. So the reason why I said, well, this part here is actually super systematic, let me just give you the ordering of what we're going to do. First thing what you're going to do, you're going to determine the ions that are produced when you dissociate, pretty much dissociate the salt. Second one you're going to do is you're going to discard off any spectators, any ones that have no chance of reacting with water, they're not going to hydrolyze. And then in terms of the remaining ions are either going to react as an acid if they're going to be positive, and they're going to react as a base if they're on the right-hand side of the table. Okay, so let's just do them all together here on the back side. You have a bunch more salts down here to figure out the hydrolysis. But let's start off here. Which of these following salts here will act as an acid in solution? First thing they're emphasizing is these are all salts. Salts are just any generic ionic compound. Salts have no business being acid or base. It has no reason why it needs to release H+ or release hydroxide. Let's just go through this procedure one by one here. Start off with Na2SO3. That's the salt. First thing you do is you dissociate. 2Na plus and SO3 minus 2. Na plus is a group 1 salt. This one here is a spectator. Don't worry about it. SO3 minus 2 is not a conjugate of a strong base. What can SO3 2 minus do? Well, SO3 minus, it can't be an acid because I don't have an H. But in the presence of water, it can actually steal a football back, right? I have this negative charge here. I'm willing to go up by an H and go up by a charge. I get HSO3 minus, and therefore ending up releasing off a little bit of hydroxide. Don't worry that we do end up forming the conjugate acid. There's so little of it that that one there won't break up again to end up forming H+. So these ones here are all weak bases. This one here will produce a little bit of HSO3 minus a little bit of hydroxide. It produced hydroxide, so therefore the pH would be bigger than 7. This one here would actually be basic. How about NH4Cl? For NH4Cl, again, first step, we're going to dissociate. We're going to get NH4 plus, and we're going to get Cl minus. I already did this for you on the other side here. Chloride is a conjugate of a strong acid. It has no chance of going in reverse. NH4 plus is actually the conjugate acid. If it's the positive that ends up hydrolyzing, NH4 plus in the presence of water ends up creating NH3 and H3O plus. Again, it's a weak acid. It doesn't break off to form too much H+, but enough to knock my pH to be less than 7. So that one is going to be acidic, so that could be one of your answers. Now getting a little bit harder here, I'm going to leave this Na2HPO4 for last. Let's do this K2C2O4. Okay. So dissociate 2K plus, and we have C2O4 minus 2 here. The K plus is a alkali salt, so this one here is a spectator. It is still going to be in solution, but it's just not going to have any chance of actually reacting with water, and therefore C2O4 minus, you can look it up on the table. Well, this one can't be an acid because it doesn't have an H. Let's react it with water instead, and this one's going to be HC2O4, go up by an H, go up by a charge, and ending up anionic hydrolysis will end up forming a basic solution, so pH bigger than 7. I saved the sort of a little bit more complicated one to last. There's actually two sort of complications I can introduce to you. One is this compound here, Na2HPO4. It's still systematic. Dissociate the salt. 2Na plus and hydrogen phosphate. The 2Na plus here is still a spectator, it's still an alkali salt. +1 and +2 salts, alkaline earth. Those ones that are going to be spectators. The problem this time is we actually find this guy twice on the table. This guy has an H, so it could be an acid. It has a negative charge here. It could potentially pick up a proton again until it ends up being neutral. The wording that we use for this one here is this compound here is actually amphiprotic. So amphiprotic, it could be acid or base. Our job is to figure out, does it want to be acid more or does it want to be base more? So let's just write out those two equations. If this one here is an acid, HPO4 minus 2 in the presence of water, as an acid, it is going to donate a proton over to water. We're going to end up with PO4 minus 3 and hydronium. The equilibrium constant for that one there would be called Ka, because it's an acid constant. That's it acting as an acid. If instead the HPO4 minus 2 actually acted as a base, same thing, reacting with water, these are already the complex equations. So as a base, it's actually going to pick up a proton from water. Water is also amphiprotic. I'm going to go up by an H, go up by a charge, H2PO4 minus, and we're going to end up with OH minus. The equilibrium constant for HPO4 minus 2 is actually going to be given by Kb. Now, although we are in general saying, yes, this one here can be acid or base, your final solution has to pick one, right? It can't be, oh yeah, sometimes acid, sometimes base. Well, we just need to decide which of these equilibrium constants is bigger, which one is higher. So I'm actually referring to the grade 12 table. We don't actually have too many of these values here on the regular table. On our IB table, we're given a few chemicals as pKa. We would need to go, well, pKa is negative log of Ka. We would then need to go Ka is the anti-log of negative pKa. But I'm just borrowing from the normal grade 12 table. The Ka of HPO4 minus is given as 2.2 times 10 to the negative 13. Right? I was expecting a tiny number to begin with, right? But this one here is actually fairly tiny, right? It's close to Kw, which is 1 times 10 to the negative 14. It's almost as bad as water at actually ionizing. Kb, even on the grade 12 table, unfortunately, they don't give you a list of Kbs. They're actually getting you to remember here. Well, we had that expression, Kw was equal to Ka times Kb, but you had to be careful. It was, these two had to be conjugates of each other. So even though this chemical by itself could be acid or base, I want to figure out, when I go Kb is supposed to be Kw over Ka, I know Kw, 1.0 times 10 to the negative 14. Do I divide by my own Ka, by my own strength being an acid? No, I need to divide by Ka of my partner, H2PO4. This one here, I'm just going to remind you, it's of my conjugate. This is the Ka of H2PO4 minus. I'm just going to quote the value for you here. H2PO4 minus gives me here 6.2 times 10 to the negative 8. Okay. So unfortunately, even my grade 12 table, it only gives me Ka values. I can do this expression 1e negative 14 divided by 6.2e negative 8. And this gives me a Kb value of 1.6 times 10 to the negative 7. And now I just have a toss-up between these two, and I can say, okay, we now have the two constants here. So how much does it want to be acid? It wants to be acid, this 2.2 times 10 to the negative 13. It's not really good as an acid. In fact, it's actually better as a base because the Kb is actually larger. This is a 10 to the negative 7. So our conclusion here is, since even though this one is amphiprotic, even though it could have been acid or base, it preferences being base, so therefore this reaction is predominant, so the predominant equation creates hydroxide, so overall your solution is basic. Since Kb is bigger than Ka, the solution produces or forms extra OH minus, right? And therefore your pH is bigger than 7. Right? We're using 7 as a dividing line because I'm always expecting that we are at 25 degrees, but that's what we do from there. Okay. I chose an amphiprotic guy where we had to compare Ka and Kb. In tomorrow's lesson, I'm going to choose a guy. Maybe the positive wants to do Ka and the other one wants to do Kb. Still the same idea. Whichever one is bigger tells you which one is predominant. The winner is going to knock the pH either into the basic region above 7 or acidic region below 7. Right? So practice through some of these questions here. Some of these would actually be buffer questions. You're going to see some hydrolysis questions upcoming as well. Thanks, guys.